All right, chapter 0. So chapters in this class are based on the chapters in our online book, MacArthur Chemistry 3A, version 1.2. Chapter 1, How Science Works. Sand can be annoying because it's so small and it is coarse and rough and irritating and it gets everywhere. Sand, like all ordinary matter, all regular matter, is composed of tiny particles called atoms. You are made of atoms, I'm made of atoms, the tables, the chairs, the walls, the air are also made of atoms. Atoms are unimaginably small. A single grain of sand, if you take a single grain of sand, the number of atoms in that grain of sand, there are more atoms in that grain of sand than there are grains of sand on the largest beach in the world. So if you went and counted up all the grains of sand on even just a small beach, Reedley Beach, right? There's more atoms in one grain of sand than all of the grains of sand that are on that beach that you'd spend the rest of your life counting out individually. And this is, at least according to chemists, among the greatest discoveries of humankind. Physicists might also think similarly. In order to understand how matter behaves, at least in this class, we want to understand how the particles that compose matter behave. So the big things that we observe, the macroscopic world, matter being big, the microscopic being small, the macroscopic world, the world that we live in, we can understand some of the way that things happen because we know how the small things work. And those small things, the way that they behave, transfers out to the bigger things. This is sort of like if you go up to a group of people, just a random group of people, and you tell them just any old joke, or you make some family reference, some inside joke, they're probably not going to laugh. It's not the right group of people. You don't know how they understand, how they interact, and so it's maybe harder to get a laugh out of them. If you go and tell a joke to your family, you know what makes them tick, you know what they like to hear, and you might be able to get more of a reaction, right? So knowing how the individual components interact, that can give us some information about how the world at large behaves. All matter is composed of atoms, which is a single particle, and molecules. Atoms, but together. So bonded together in groups are molecules. We'll talk more about these later. Part of this understanding is, we'll use H2O water as an example. The actual shape of water is seen over here on the left. These are hydrogens in white, and we've got an oxygen in the middle. This is the actual shape of water. If you were just to construct it without knowing anything about water, the way that you might put it together is in a straight line, like this, with the oxygen in the middle, the hydrogens on the side, and that would be a perfectly reasonable thing to assume for the shape of water, having no idea about how atoms and particles interact and behave. But the difference between these two shapes is the difference between living and not living. The difference between having fish in our lakes and not having fish in our lakes. The difference between existence and not existence, just based on the shape of the molecule. Because water is shaped this way, because it's got this bent configuration, we live, we breathe, we have life. If water was instead this other configuration, life as we know it wouldn't exist. There is also a connection between the atoms and molecules that we experience every day. There's supposed to be an image here. I didn't put it in. And we chemists, you're sort of chemists now because you're taking a chemistry class, we look at and explore this connection between the atoms and the molecules that we know are there because physicists tell us they are, chemists tell us they are, and the world that we experience. So we're trying to understand how matter behaves. So things that have mass and occupy space. atoms, molecules, people, chairs, tables, walls, air. We try to understand how those things behave by studying the atoms and the molecules and how those things behave. Everything that you can hold or touch is made of chemicals, strictly speaking. We wouldn't consider them chemicals, probably most of us, but technically it's chemicals. Your chemicals, I'm chemicals, the walls, tables, chairs, air, etc., the water, those are also chemicals. Chemicals make up virtually everything that we come into contact with, literally everything we come into contact with. The void that's between the molecules and the air is not chemicals, because it's empty space. However, the popular conception, the one that you're probably familiar with, is that chemicals are dangerous. So the popular conception, dangerous poisons or pollutants, or artificial flavors and preservatives, and red 40, which the fish long for. So we've got some pictures of chemicals and sewage, because chemicals might also be in there. If you've been to a Blaze Pizza, I like Blaze Pizza because of their pizza, but the last time that I went was a long time ago. They had up on their wall, no chemicals ever, meaning that they don't use like artificial flavors and preservatives and stuff. They're kind of Whole Foodsy in that way, right? They're completely wrong. It's all chemicals always. Pizza dough, the tomato sauce, the pepperoni, the cheese, it's all chemicals. All chemicals always. But maybe no dangerous chemicals. Maybe no things that are bad. So ordinary things are also chemicals. And here's that pizza picture that I included because of Blaze Pizza. Shout out Blaze Pizza and your sign that's incorrect. So ordinary things like the water we drink, the air we breathe, the food we eat, medicine, and our bodies, those are also chemicals. And chemists are very interested in why things are the way they are with respect to chemicals. Within science and chemistry, there's a general way of thinking that's the scientific method. We don't use this all the time in the strict formal sense. We don't draw out our flow chart and our diagram for the scientific method, but we kind of follow some of these principles, and you can use these principles yourself. You probably have, and you just didn't know it. So the scientific method really emphasizes observation and experimentation. Observation, seeing something, tasting something, hearing something. Experimentation, trying something. Running a little experiment. It's not a rigid procedure. It doesn't automatically lead to a definitive answer, but it does give us kind of a pathway of working through some problems and trying to figure out whether our guesses were right, essentially. It's different from ancient Greek philosophies that emphasized reason. Not everything follows with perfectly logical reason in the real world, or at least it's not reason that we can see or interact with all the time. And so the scientific method is helpful there. There's 4 key characteristics. Observation, typically something involving senses. A lot of the time in chemistry and science, at least nowadays, it requires expensive technical instrumentation a lot of the time, at least for chemistry. If you're in ornithology, the study of birds, maybe you don't need expensive instrumentation, you just need a pair of binoculars, and you need to go out into the field and count birds every day for a year, maybe. There's also going to be formulation of hypotheses. Hypotheses often, there's a different word or phrase for it, but just a guess. A hypothesis is just a guess. You test those with experiments. I don't think I need to explain experimentation. And then we can formulate laws and theories. We'll talk about those later. So laws and theories, we'll discuss those a little bit later. And this is sort of one way that we might map out the scientific method. So we're going to start with typically observation. We notice something, maybe it's the food in the pantry always has mold in it. Like we store our flour in the cupboard and it always has mold in it. We just store it in the bag. Why does it get moldy so quick? It's supposed to be shelf stable. It's supposed to be fine. This is just trying to give you an example of what this might look like in your life, right? So we've got moldy flour in the cupboard. We might come up with a hypothesis about why the flour is moldy. Maybe there's an evil actor, like somebody who acts, that actually didn't help at all. Somebody that's just nefariously sneaking into our kitchen at night, maybe they're a clown, and they're planting mold spores and water in our flour. That seems like a pretty outlandish hypothesis, so it's probably not true, but evil clown planting mold. Very unlikely. We could conduct some experiments or some follow-up observations. We could, maybe if they only plant the mold in our cupboard, right, we try storing our flour somewhere else. We store it in the fridge, we store it in a box in our bedroom, and we wait and see if it gets moldy. Or we store it in a safe where the evil clown cannot get to it. And we discover, yeah, it doesn't get moldy there. Okay, so there's something special about our cabinet. We put it in a safe in our cupboard, even better, because the clown, we definitely know, has access to our cupboard, but can't get into the safe, so our flour should be fine. So, or we just lock our house at night so the clown can't get in. Anyway, I'm being weird. So a realistic set of observation, hypothesis, experiment, maybe we just have water intrusion in our cupboard, right? So we get a hygrometer, something that tests the water content in a space, or we check our relative humidity in our cupboard. It's a little bit moist in there. We can investigate and see maybe there's something else going on there, right? So it's stuff that you might kind of think through. This is just kind of a formal process or a formal outline for how we might go about these steps. From the experiments, if they're correct, right, we might, if we've got enough to generate a law or a theory, a model, we'll talk about those again later. Or it might take us back to square one. We might have more observations. We might redo our hypothesis because the evil clown thing didn't work out. Maybe it's just a wet cupboard, or we're not storing our flour correctly. So our first step is typically going to be an observation or a measurement. Some of these can be made with the naked eye, like mold in the flour or almond milk going bad in the fridge, or other things like that. Others rely on the use of sensitive instrumentation. That can be very expensive or not very expensive. Not very expensive in my mind, 5 figures. Very expensive, 6 figures or 7 figures. So $1 million, $500,000. That in my mind is expensive. Not expensive, the stuff that we're going to be using, maybe a little bit in future labs if you take 1A, 1B, or OChem. Stuff costs a lot of money. Usually for observation and measurement, there's going to be a measurement or a description of some aspect. Moldy, red, coarse, solid formed, something like that. And usually it's going to be more than one word. The idea behind descriptions and observations, we want to write out enough information that somebody who didn't see it, who wasn't there, would kind of know what was going on and would know that they're seeing the same thing that we're seeing. An example of an observation, Antoine Lavoisier, French, from the 1700s, studied combustion, burning stuff by, you guessed it, burning stuff. He burned stuff in closed containers. So we've got a picture of, or a painting of Antoine, and this like contraption here on the table. That's what he was burning stuff in. So a closed container, like a jar, essentially. He'd put stuff in there, light it on fire, close it up real quick, and he observed the mass of the container and its contents did not change during combustion. So burning did not change the mass, or what we would think of as weight. So we weighed the container before and after burning it, and it was the same weight, which is not what you expect, because when you burn stuff, what happens? It goes away, right? If you burn stuff in your fireplace, it goes away, but you're not burning it in a closed container. Antoine was burning it in a closed container. Those observations can lead to the formation of hypotheses, tentative explanations, an educated guess. That's the word I was thinking of, the words. Or a best guess. In order for us to have a good hypothesis, it needs to be something that we can prove wrong. So it needs to be something that we can say definitively, or could say definitively, yes, this is wrong. If I tell you that an invisible clown that can't be detected is causing the flour to go moldy, it's an invisible clown. There's no way of telling that the invisible clown is there or not. You can't prove that it's wrong. It's a bad hypothesis. It has to be something that we can prove is wrong. The cupboard is wet. Somebody keeps pouring water in the flour in the cupboard, right? Those are things that we can prove wrong. You just test whether there's water in the cupboard. So Lavoisier, that we were talking about earlier, hypothesized that combustion involved the combination of a substance, what he was burning, with a component of air. So air is a mixture of a bunch of chemicals, a bunch of gases. One of those he assumed was reacting and causing the burning to happen. Hypotheses are tested by experiments. The more controlled, the better. So when we're doing experiments, we want to test ideally just one thing at a time. If you change 15 different things, if my car, for example, is running a little bit weird in the winter, it's running a little rough, and I decide, well, I want to see if it's something wrong with my car, I just test somebody else's car. I drive someone else's car, it doesn't run rough in the winter. All that I know is my car runs rough. I haven't really helped do anything with my car, right? I could try changing the oil if I haven't changed the oil in a while. Maybe it needs I need to put in some like gas stabilizer or fuel injector cleaner, right? I would want to change one thing at a time, see if it runs a little bit better, and then that helps me narrow down the list of things that I have to go and tell my mechanic to check. Or you just take it to somebody and they fix it for you. But they would be doing this. They would be checking one thing at a time based on what they know. And these experiments can be designed to validate, to go along with your hypothesis, or try to prove your hypothesis wrong. If the hypothesis is incorrect, changes can be made. Right? So maybe the cupboard is not actually wet. Maybe there's not a lot of water in the cupboard. So we have to change the hypothesis. Maybe the flour is getting wet in some other way. Maybe our countertops are just always wet. And so setting the bag of flour down on the countertop, it's absorbing moisture from there. So maybe we just make sure that we dry our countertop every time we pull the flour out. Right? We can change our hypothesis in little ways. The wetness, of course, just being because mold likes water. If we get a lot of similar observations, that can lead to the development of a scientific law. If X happens, then Y happens. It's like a very simple way of boiling it down. If I see this one thing happening, then this other thing is going to follow. It's essentially a rule. When I was a kid, if and then snuck out and played video games when I was supposed to be sleeping, then I would get grounded, or I would get in trouble some other way, right? That was just kind of a law of the house. If I did something that my parents said I wasn't supposed to do, then there would be punishment. No explanation of why there's the punishment or why the rule is there in the first place. So there's no why to scientific law. It's just if this, then that. We can also subject these to experimental testing. But there's no why to a scientific law. It just states what happens, and sometimes it'll state when it happens. So Lavoisier developed the law of conservation of mass, an important one for our class. In a chemical reaction, matter is neither created nor destroyed. An example of a chemical reaction being burning. Or combustion, as we might otherwise call it. So he was burning in that closed container. Because it was in a closed container, everything, all the gases, all the smoke was trapped. So it was still in the container. He burned it. It changed shape. It's changed what it looked like. But when he did it before and after, it had the same mass. So he knew that matter wasn't being destroyed. New matter wasn't being created. The mass didn't change. The law of conservation of mass is one that you'll want to know. Additionally, we can also get scientific theory. And a scientific theory has a why. Has a why, or is the why. So this can provide an explanation. Our laws provide an explanation, just like the laws that we have in California, in Reedley College, in the United States. Don't tell us why those laws are in place. They just say, if you drive a certain amount over the speed limit, or if you drive over the speed limit, you will get a ticket. Why do we have that in place? The law doesn't necessarily say. The reason is order, stability, whatever, so that people don't die as much driving, right? Laws generally are in place to, some of the laws at least, are generally in place to keep us safe, to help society function a little bit better. No killing people. It's bad for society, right? So a lot of the laws at least, are in place to keep us safe. Not all of them, but some of them, many of them. And theories, these are the explanations that are beneath that. They can predict behavior beyond the observations, which is super helpful. So they've got more power in many ways than our laws, our scientific laws. We can also subject these to experimental testing. Lavoisier's law led to John Dalton's atomic theory. A lot of times things that are important are bolded. And that theory said that all matter, things that have mass and take up space, was composed of small indestructible particles called atoms, which we'll talk about more in future chapters. Might even be chapter 4. Switch my numbering at some point, so I don't always remember. All right, so a summary of laws versus theory. The law states what happens, and the theory explains why those things happen. Both of them come out of observations, maybe hypotheses. They can both be proven false. Scientific laws and theories do sometimes get thrown out or modified or updated. And theories, in many cases, are better. They tell us why things happen. So if my parents have a rule of no running with scissors in the house, right, that would be a law. The theory, they want to keep me safe. right? They don't want me running around with scissors because I might stab myself in the leg, I might stab myself in the face if I fall. And so I could maybe, even if they don't have rules about no setting off fireworks in the house, setting off fireworks in the house is dangerous. So with my theory of they want to keep me safe, I could hypothesize if I set off fireworks in the house, they're also going to get mad at me, right? I'm going to get in trouble for setting off fireworks in the house, even though there's not explicitly a rule against that. To succeed. Here's a fun quote from Nobel Prize for Chemistry winner Roald Hoffman. I like the idea that human beings can do anything they want to. They need to be trained sometimes. They need a teacher to awaken the intelligence within them. But to be a chemist requires no special talent. I'm glad to say anyone can do it. And what's that last part say? With hard work. So there's hard work involved in succeeding in chemistry. That's true for most people. The vast majority of people, there's a lot of hard work involved in succeeding in chemistry. It's not an easy subject, again, for most people. You might be one of those people. Congratulations. Glad to have you here. The rest of you, still glad to have you here, but you're going to have to work hard to succeed. But you can succeed. And that's the end of chapter 0. Any questions? Big takeaways. Law of conservation of mass, difference between laws and theories, and atomic theory, which I think we come back to later. So those are some of the big takeaways from that chapter.